a warm welcome to all for the virtual workshop on computer-aided drug design organized by Department of Biotechnology, St. Peter's College of Engineering and Technology. I find immense pleasure in introducing our honorable chief guest, Professor Mukesh Doble. He was a prestigious student of IIT Madras since 1967 and have also completed his master's in chemical engineering in the year 1974. He also played a vital roles in NCC, Boy Scouts, etc. He then got his graduation in PhD from University of Aston, UK in the year 1980. Stepping into the research experience, he then worked as a postdoctoral research associate in Chemical Engineering Department of Cambridge University in 1980, followed by research associate in Texas A&M University in 1988, program manager in ICA India R&D Center, Mumbai in 1989, and program manager in GE Research Center, Bangalore in the year 2000. Finally, he started his career in teaching in 2003. He was a man highly endorsed for his drug designing, biomaterials, and biopolymers. Owing to his high profile and endorsed skills, he landed in IIT Madras as a professor in the year 2004. He had publications of around 224 journal articles and authored 3 books. He was also honored with 3 awards in the year 2000, 2002, and 2004 respectively. He have guided more than 11 doctoral theses. Finally, a man with extended profile will take over the session with this expert topic, computer-aided drug design. Wish for all the participants to get benefited out of this virtual workshop, and thank you all.
Now I request Ms. K. Harini to say a few words about this workshop organized by Students Chapter.
Now the session can begin.
Okay.
And Sir Doble, sir?
Yeah.
Yeah, let's start with the session, sir.
Okay.
Thank you.
Good morning, everyone. It's a pleasure to be here. Thank Dr. Suri Lakshmi for the invitation. I'm going to take 4 days talking about various aspects of drug design using computational tools.
Excuse me, sir. Sorry
Yeah.
for interruption. Participants, a little announcement. Mr. Devanathan Venkateshan, please maintain the decorum in the comment forum, okay? Please switch off your video. Thank you, sir.
Yeah. Can you see the screen? Can you all see the screen?
Yes, sir.
Full screen? Yeah. So I'm going to talk about 4 major aspects on the 4 days. So maybe I'll take about 1.5 hours or slightly more than that. And then you could even practice it the rest of the time in the afternoons and evenings. Okay, so first today I'm going to talk about what's meant by a drug. What are the various properties for a molecule to be called a drug? So there are some things called ADME rules: absorption, distribution, metabolism, excretion. So we will talk about those rules. How do we predict properties? Okay, then we look at many databases which give a lot of properties of molecules and even drugs. So we will look at some of those databases. So that will be on the first day. Second day, we will look at pharmacophore modeling. That's called ligand-based modeling. Pharmacophore is structural features that are necessary for some activity of a molecule. So we will look at pharmacophore-based modeling. What are the structural features that are necessary for activity? Third day, we will look at quantitative structure-activity relationship, QSAR, quantitative structure-activity relationship. Okay. And then the fourth day, we will look at homology modeling and docking and so on. Okay, so that is target-based design. So the second day and third day it will be a ligand-based design, and fourth day we will look at target-based design. Okay, of course there are some areas which are not covered, which are slightly advanced, and I am going to show all softwares that are available in the net free of cost. So you don't have to purchase any softwares at all. So we can look at all the softwares that are freely available, and you can make use of for all these aspects, whatever I'm going to talk about in the next 4 days. So that's the advantage of this. You can use it for your teaching purposes, or you can use it for your even research purposes. So all the softwares that are freely available. Okay. So that's what we will cover about actually. So today we will talk about drug properties. What are the necessary requirements for a molecule to be called a drug, and then various databases which gives these properties and so on actually. Okay. Okay, can you all see the screen, full screen? Please somebody give a feedback.
Sir, your screen is not visible.
Not visible. Yeah,
No,
I'm
sir.
having problem with your not fully visible.
Yeah, yes, sir.
No, sir.
Yeah, okay. Now,
Yes, sir.
full screen.
Yes, sir.
Okay. So this is an interesting picture which talks about how drug discovery happens. So initially, a lot of computational tools are used for designing drug, especially if you want to look at the mechanism of action, if you want to look at targets, if you want to get proteomics. So all these are computational based approaches. Okay, then you start looking at possible candidates. That's called lead identification. That is a possible candidate could be a drug, but it may fail because of so many reasons. It could have toxicity, side effects, so many things. You must be hearing about it in the past 6 months, right? New drugs for COVID, but then halfway through it stopped because it could be some toxic, it could be some side reaction, or it could be having some synergistic interaction with something else. So many compounds may fail as you go along into the clinical, preclinical trial and all that. So here is where our focus is on lead identification. That's molecular modeling, QSIR, drug likeness property, toxicity, ADME. So here we use, you can see these two arrows here is where we use various computational tools to identify leads. We optimize leads, that means find out best leads with best properties. So here we use a lot of computational tools. So computer-aided drug design is not bioinformatics. Bioinformatics, proteomics, they come before. That's looking at target protein, looking at the sequence of the proteins, looking at the 3D structure of the protein. So that's bioinformatics. So that's earlier, but the focus of my computer-aided drug design is on the lead identification, molecular modeling, and then looking at drug likeness property, toxicity, ADME, and so on. Okay, so this is our focus, where I have put in some arrows actually. And then once some good leads are found in computation, then you may test it in your lab. We call it in vitro studies, wet lab studies. And then once you have some candidates, you may go into preclinical and clinical trials. That could be based on animals. Preclinical is animal trials. Then clinical trials could be human-based trials. So lead identification, optimization of lead, looking at toxicity, using computational tools is what our focus on. Okay, so can a molecule be a drug? Just because a molecule shows very good activity does not mean it can become a drug, because so many things, because it's being consumed by a person, sick person, for a very long period of time. So there could be many aspects one need to consider. Water solubility, because a drug, when we take it orally, it has to be soluble in our stomach, right? So that is important. Otherwise, it may go and sit like a stone inside our stomach. Intestinal absorption. Most of the oral drugs go to the stomach and then they have to get absorbed. We call it GI absorption to the bloodstream. So will it get absorbed in the intestine? Blood-brain barrier. There is a barrier which separates the blood, which is flowing throughout our body and the brain, because the brain does not want to get viruses, bacteria, toxic chemicals which are present in the blood into the brain. So there is a barrier which separates that. So we don't want all the drugs to cross the blood-brain barrier. So we need to check. Release at specific site. You want the drug to be released at a particular place. If there is a tumor, the drug has to ideally go and attack the tumor, not all other cells. As you know, if you look at some anti-cancer drugs, they may be toxic to the healthy cells also. That's why people who have chemotherapy also have a lot of side effects, because the drugs go and affect the healthy cells in addition to the cancerous cells. Non-toxic. Drugs should not be toxic. Short-term toxicity, long-term toxicity, then we have genotoxicity, nephrotoxicity, so many different types of toxicities. Long-term use, because if somebody is having a blood pressure, they are going to take the drug for a very long time. If somebody has a diabetes, they may take some drugs, diabetes drugs, for a very long time. So can it be used? Metabolites also non-toxic, because not only the drug, inside the body, especially in the liver, many drugs get metabolized. Almost all foreign molecules get metabolized. So the side products or metabolites should not be also toxic. That is another problem. And then excretion. That's very important. After the drug has done its job, it should come out of the body. It should not remain inside the body and keep staying for a long time. That's called excretion. So it should slowly come out. Otherwise, it may build up, even if it could be parts per trillion over a long period of time. If it doesn't get excreted, it gets built up. That could also have problems, actually. So we need to look at all these aspects. Okay. So when I take a drug, it goes inside stomach and then goes inside GI. Then you have the small intestine, large intestine. So it gets absorbed, it gets metabolized, and then finally it goes to the liver region. Liver, a lot of enzymes are there where metabolism takes place. So drug gets metabolized. Then if it comes to kidney, especially hydrophilic or water-soluble molecules, it comes out as excretion. Drugs which don't get absorbed in the GI comes out again as fecus, so that's also lost. And then it goes into the bloodstream. So some drug may get absorbed into the plasma region, plasma proteins, and then finally it reaches target site. So if I take a drug orally, by the time it reaches my target site means it could be, I may be having a swelling in my hand, in my finger, that's my target site. If somebody has a tumor in some part of the body, that could be a target site. or somebody has a fungal infection in the toe, that could be the target site. But you may be taking the drug orally. So by the time it reaches, many things are happening inside. So a drug should satisfy all those conditions. That's very, very important. That's why many compounds fail, although it may work very well in the lab because of so many things. Oral absorption. Mostly everybody likes to take oral drugs, not intravenous or intraperitoneal or intramuscular. So drug has to be absorbed efficiently from the stomach into the blood or from the small intestine. Volume of distribution. The drug goes into the bloodstream, so it gets distributed throughout the bloodstream and starts traveling. The metabolism in the liver. Then we have enzymes like oxidoreductase, lipases, esterases, amidases. So many enzymes are there. So your drug can get metabolized. The excretion, like I said, not two types. One is fecal, the other one is through the urine from the kidney. Solubility at different pH. Okay, your stomach has a very low pH too, whereas as it travels to the duodenum, then it goes to small intestine, then the colon, pH starts increasing. So the drug has to be soluble at all these pH places. Otherwise, it will not be getting absorbed in that correct place, right? Then there is something called bioavailability. Like I said, I take some drug, say 500 milligrams of ibuprofen. What it reaches to my target may be much, much less. Okay, you all know ibuprofen is used for inflammation. Okay, so you may take 500 milligram, but what it reaches at the target site may be much less because of so many things happening. This ratio is called bioavailability. Okay, so what may be reaching could be 1 milligram. I may be taking 500 milligram. What may be reaching 1 milligram. Actually, 500 milligram, when I say it's not the active drug, it could be binder, it could be colorant, it could be antioxidant, it could be so many other things, solubilizer and so on. So the active ingredient maybe say 10 milligram. What reaching at the target site is 1 milligram. So the bioavailability is 1 by 10, that is 10%. Okay. So the bioavailability also has to be very good. What the drug amount that's reaching at the target site. It should not have side effects. Like I said, it as you know, some of the cyclooxygenase 2 drugs, cyclooxygenase 2 is an enzyme in the inflammatory pathway, and drugs which were discovered and used about 12-15 years back had cardiovascular side effects. Okay, so it should not have side effects. It should not be toxic. Different types of toxicity. It should be stable at all pH. When it goes to stomach, where pH is 2, drug should not get degraded because of such low pH. Okay, that happens. Many drugs can get degraded, especially if there are some ester type of bonds. It can get degraded at very acidic pH. Then we have the blood-brain barrier. Like I said, it should not cross the blood-brain barrier and reach the brain. Then it may disturb the brain functions. If we are taking a say the inflammatory drug for your inflammation in your finger, the drug should not go into the brain and affect the brain activity. Okay, so then there is a set of proteins, almost 50 proteins called PGP, glycoproteins. Okay, these are glycoproteins. They act as efflux pumps. They actually capture any xenobiotics that are present in the blood. Xenobiotics are toxic chemicals, and then they throw them out into the excretion pathway. Okay, so they act as this type of effluxing. We don't want your drug also to get captured by the PGBs and then get effluxed out. So many things we need to consider. Okay, so this is what I said. Bioavailability is concentration at the target site and the drug amount we take. So into 100. That's called bioavailability. So generally 35 above is good. If the bioavailability is very large, then you can give very low amount of drug because the amount will reach the target site. If the bioavailability is low, then we have to take more drug. That means it could have side effects, toxicity, and so on. So ideally, bioavailability should be high. Say if you take metformin, you may be knowing is an antidiabetic drug. It's got a very good bio, almost 70%. If you take a Taxol is an anti-cancer drug. Okay, it's taken for certain types of cancers. It's got very poor bioavailability. So if a doctor prescribes such medications, they have to prescribe very large doses. Some of the antiviral drugs, they have poor bioavailability. Their water solubility is low. Even anti-malarial drugs, and the bioavailability is low. So bioavailability is a very important parameter. We can find out when we do animal studies bioavailability. There are some software which can predict also. I will show you one or two software which can predict. Okay. Okay. If you look at the physiology of the gastrointestinal tract, the stomach, the food remains for only 30 minutes. Surface area is 0.1 meter square, and pH is very, very low. Okay. When you have fed state, pH increases. That's why sometimes doctor says take the medicine before food, take the medicine after food, because sometimes when the food is inside the stomach, pH changes, so the absorption of the drug also changes actually. Then geogenome, it remains longer. Ileum and colon, this is the large and small intestine, it is much longer. Geogenome, the area is very high, so absorption also could be high. pH is also high. So this is a very important parameter, because if you want to have fast acting drug, you want the drugs to get absorbed in the stomach. That means it should be absorbed at this particular pH condition. Okay, so the pKa, you all must have heard of pKa. You must have studied in your chemistry. pKa is the pH at which there is a dissociation of the molecule. Okay, so it should match with this pH so that it gets absorbed. It should not be dissociating at this pH, because once a molecule dissociates, it becomes anion and cation. So it will have very high charge, and your GI is very hydrophobic, because GI is made up of lipids. So it's very, very hydrophobic. So the absorption will be poor. So we don't want the drug to get dissociated at this pH, so that it will get absorbed in the stomach. So fast acting drugs, it will be highly water soluble. It will not get dissociated at this pH. Like some headache medicines or fever medicines will be fast acting, whereas some slow acting anti-malarial drugs could be slow acting. Okay, so you need to understand the pKa, that is the pH at which they dissociate, and we should understand the solubility of the drug if you want to design fast acting and slow acting drugs. Again, the surface area is also there, which plays a very important role. So in human stomach, most acidic drugs and very weakly basic drugs are absorbed, because acidic drugs in stomach pH is 2. So when we say pH is 2, that means there is a lot of hydrogen ion concentration. So acidic drugs will not get dissociated. So they will remain as a drug and get absorbed. If it dissociates, it may form, like I said, cations and anions. So it may not get absorbed actually. So like I said, aspirin and so many drugs, they get absorbed in the gastric region actually. Okay, whereas if you look at anti-malarial basic drugs, okay, so they will go down into the intestine to get absorbed. So these aspects also one need to consider when you are doing drug discovery. So we should know the pKa of the drug. We should know the water solubility of the drug actually. Okay, so there are many structural features which affect the activity. Molecular weight of the structural features means we call it structural features, structural descriptors. So many things they are called structural features. The molecular weight, hydrogen bond donors. Hydrogen bond donors are OH, NH. That is, OH is a hydrogen bond donor. NH is a hydrogen bond donor. Hydrogen bond acceptor could be nitrogen or oxygen. Okay, without any charge. They are called hydrogen bond acceptors. Log P. Log P is a I will talk more about log P later. Log P is a hydrophobic hydrophilic balance of a molecule. Why these two are important? There has to be a balance. If it is more hydrophilic, that means it's more water soluble. We want the drugs to get water solubilized. Orally, we need the drug to be water solubilized. But if it is more very hydrophilic, when it goes inside the stomach, it will not get absorbed and go to the bloodstream because the GI, that is gastrointestinal tract, is lipid, which is very hydrophobic. So we want the drug to be a little bit hydrophobic. So it should also have hydrophobicity so that it gets absorbed in the stomach. It should also have hydrophilicity so that it solubilizes in water. So that balance is very important. It should not be too much hydrophobic. It should not be too much hydrophilic. If it is too much hydrophilic, it will very well solubilize, but it will not get absorbed in the GI. If it is too much hydrophobic, GI absorption will be good, but it will not be water soluble. So log P is a very important parameter. I talked about the pKa, that is the pH at which dissociates. Similarly, for acidic, pKb is for basic. Polar surface area. Polar surface area is also related to hydrophilicity. Okay, polar surface area, if it is polar, it's very hydrophilic. If it's non-polar, it's very hydrophobic. Number of heterocycle groups it has, like nitrogen groups that is present, or sulfur groups, they are called heterocycles. How many aromatic rings, that is benzene rings, how many ketone groups are there, how many rotatable bonds are there, what is the crystalline nature. If it is too much crystalline, it's not going to get solubilized in water. Amorphous is good because solubility is good. How many ester bonds are there, how many amide bonds are there, is it in neutral form or salt form. Salt forms are more soluble in water, neutral forms are not soluble. That is why 70% of the drug are always in a salt form, potassium salt. For example, if you take any antibiotic, they will always be in a salt form. Now, all these left-hand side features, we call it structural features, structural descriptors of a molecule. They affect the right-hand side. Activity, selectivity, absorption. It is not one-to-one, but it could be one-to-many actually. See, log P, which is hydrophobic, hydrophilic balance, could affect oral absorption. It may affect bioavailability, which is coming at item number 8. So it may affect many things. So it's not just one-to-one, but one-to-many. Okay, molecular weight could be affecting absorption because very big molecules may not get absorbed. Small molecules may get absorbed. Okay, so one-to-many hydrogen bond donors, it may get binding to the target site well. Too many hydrogen bond donors, it may be very water soluble. All those things can happen actually. Okay, so as a medicinal chemist or a biochemist or a synthetic organic chemist, you can modify the left-hand side, which will affect the right-hand side. That is how the lead optimization is done. So if you find your drug has poor bioavailability, possibly because the water solubility is low, then you may add some hydrophilic group like oxygen, nitrogen into the structure, and then improve the water solubility. But it is not that it is so easy, because if you improve water solubility, then its absorption may get disturbed. It may not get absorbed, bioavailability may go down. So you need to balance many things when you are doing a drug discovery. Okay, when you are doing a lead optimization, that's a very important point. So because it is nothing like one-to-one, but it is like one-to-many. That's a very important point we need to keep in mind. So you look at this, most of the drugs fail when it comes from lab into the preclinical. You must be reading in the present situation also. They say this drug we are going to test, and then they say there is some problem. So most of the drugs fail. Even if they test 100, only 3 or 2 may pass. 97 may fail. We are talking about new drugs. I'm not talking about old drugs, which are called repositioning. Suppose there is an antiviral drug which is used for HIV, and they are testing for, say, SARS, the current problem. Then that's called repositioning. Whereas I'm talking about new drug discovery. Okay. So most of the drugs fail. 40% because of poor absorption, distribution, metabolism, excretion, ADME properties. 30% fail because of lack of efficacy. When I give it in animal or human, it's not showing so much activity. Maybe because of bioavailability or maybe degradation, so many things. 20% fail because of toxicity. So if you add up all these, almost 95% fail because of the properties of the drug. Okay? The properties which I showed you in the past few slides, that is affecting the either poor biopharmaceutical, it's leading to toxicity or side effects. So one needs to look at all these simultaneously when you are designing or discovering drug in the lab. So it's not that once upon a time we tested the drugs for some disease and we said, oh, it's working very well, we'll go to animal studies. Such approach is totally now wrong. So we need to simultaneously check whether it satisfies all the drug likeness properties, ADME properties, bioavailability, whether it has got any toxicity, side effects, all these simultaneously before one goes into animal study. So how do you check? There are softwares which can do. You can also do some in vitro studies using cell lines. You can also do animal-based studies using small animals, rats or mouse and so on. Okay, before going into human trials, because human trials cost you a lot of money and it takes a long time. Okay, so this log P I talked about, it's a ratio of logarithm of octanol water. Octanol is taken as hydrophobic, water is hydrophilic. So octanol means if more drug is in octanol, that means it's hydrophobic. If more drug is in water, it's in hydrophilic. So we take a logarithm of the ratio of octanol to water, and that's called log P. So if more is there in octanol, log P will be high. If more is there in water, log P will be very low. So this is a ratio of hydrophobic, hydrophilic balance. Hydrophilic is soluble in water, blood also, because blood contains 70–80% water. So hydrophobic is because it has to cross the GI membrane. That is, we are talking about oral drugs. If it is too much hydrophilic, like morphine, for example, it cannot be taken orally. So what they do, they inject it. So when you do injection, then log P is not a big deal at all, because we are not talking about oral absorption at all. Typical values for log P for most of the compounds are -3 to +7. -3 means very hydrophilic, water soluble. +7 is all very hydrophobic or lipophilic. So most of the drugs, they have seen that log P falls between 2 to 4. Okay, most of the drugs. Okay, so if you have found a molecule which works in the lab, you check the log P, and if it is not in this range, then you are sure that it will have a very poor oral bioavailability. You better do some change. If it is very much low, less than 2, then make it a little bit more hydrophobic. Or if it is more than 4, make it a little bit more hydrophilic. Okay, so that's a very important point to keep in mind. Okay, there are many rules. I'm going to show some rules, and the softwares also give many rules. Lipinski's rule, Mukesh et al. Rule, Weber rule, blood-brain barrier rule. So many rules are there. Opera rule of 3. I'm just going to show you a little bit of these, and many softwares also calculate all these rules also. So Lipinski is a person who worked in Pfizer, and he looked at many drugs and found out some commonality, and he said if a molecule you are discovering in a lab follows these conditions, then possibly it will have good oral bioavailability. Okay, so he said molecular weight should be less than 500. Okay, we are not talking about proteins and so on, because most of the, suppose you have protein based molecules, then chances are it is never given as oral. It will be given as an intravenous, as a chemotherapy and so on actually. So we are talking about small molecules. When we talk about small molecules, molecular weight less than 500, number of hydrogen bond acceptors less than 10. Acceptors are nitrogen and oxygen. The number of hydrogen bond donors, that is NH and OH, less than 5. So, and then log P should be less than 5. So this is what is Lipinski's rule of 5 means actually. So if you have a molecule, check whether molecular weight is less than 500, number of hydrogen bond acceptors less than 10, number of hydrogen bond donors less than 5, log P less than 5. So if any of these conditions are not satisfied, so it might not have a proper absorption, GI absorption. So do something about it. actually. So you can modify some of this. And then there is something called Gauss et al. Rule. So he came up with some other numbers. You can see, you know, log p, some numbers. Then they said molecular volume for something, molecular weight. Lipinski said less than 500, whereas this person says between 160 to 480. Number of atoms. So he Gauss et al. Comes up with different set of conditions and say, please check whether your molecule satisfies these conditions. Okay. Then came Weber rule, another person. He said number of rotatable bonds which are rotating. Why is this rotatable bonds important? Because rotatable bonds gives different conformation to molecules, and ultimately molecule or drug goes and binds to some target. Okay, if it is a so if it has got a lot of movement, it should have some movement so that it can go and bind into a target active site of a protein. But if it has got too many movements, it may go inside, then come out. It may be so flexible, it might not form a rigid ligand protein complex. So they gave some number. And then they also said the polar surface area should be less than 140 angstrom per air. Like I said, polar surface area is an indication of the water solubility. So we don't want too much water solubility. And then they also said the number of hydrogen bond donors and acceptors less than 12. So he came up with another rule, Weber rule, they call it. Then there is something called Mukesh rule. He came up with some other things. Okay. Then we came up effective permeability. That is called effective permeability rule. He came up with something else. They said the polar surface area, its effective permeability into the stomach is a function of polar surface area and hydrogen bond donors. Okay, so he came up with the equation which tells you the effective permeability into the stomach. Then there is something called blood-brain barrier, which I mentioned. Okay, blood-brain barrier composed of very high dense cells. Okay, it restricts passage of substances from the bloodstream much more. Okay, so it permits only oxygen. It permits only nutrients like glucose. It stops viruses. It stops bacterial and many things. So it will stop very charged molecules, salts, and so on. Actually, so the idea is it keeps the brain in a proper condition, away from rest of the toxins, xenobiotics, viruses, and bacteria, and that's called blood-brain barrier. So there are some rules for that also, blood-brain barrier also. Okay. So there are some rules which says if the molecule has certain properties, the blood-brain barrier penetration will not happen. If the molecules does not satisfy these conditions, then your drug may pass through the blood-brain barrier, and so on. Actually, so many rules are there. Some softwares give you those rules. Then, like I mentioned, there is a set of transporters, efflux transporters, P-glycoprotein efflux transporters, which throws xenobiotics out into the excretion. So sometimes it may capture the drugs as a xenobiotic and throw it out. So we don't want our molecule to get thrown out. Okay, so we need to look at conditions which will prevent the drug as a part of the efflux system. So there are some conditions here. You can see nitrogen plus oxygen. If it is greater than 8 and molecular weight greater than 4, pKa greater than 4, then it could be thrown out by the efflux pumps. If the nitrogen plus oxygen less than 4, molecular weight less than 400, pKa less than 8, then it might not get thrown out. So you can see so many rules are there, and each rule sometimes may be contradicting with each other. So when you design for some condition, maybe some other condition might not get satisfied. So it is not a straightforward. That is why a lot of lead optimization comes into the picture, and that is why many times, sometimes when you design drugs in the computational tool and then you go into the wet lab, or when you go into animal studies, many drugs fail because of this. So many rules are contradicting with each other, and so you need to balance many of them actually. If you improve solubility, you may have GI problems. If you improve GI problems, solubility may get disturbed. If it is a very small molecule, then it may be a PGB efflux transporter, and so on. So if it is a nitrogen containing molecule, it may improve the hydrogen bond acceptors, but it may be toxic, and so many things will contradict with each other. So we need to keep balancing many of them. Okay. That's the biggest challenge in drug discovery. Okay, so there is another rule called Oprea rule of 3 molecular. So look at this. These people came up with molecular weight less than 300, whereas Lipinski's rule, if you see, less than 500. Okay, so it is not that you have to exactly follow all the rules all the time, but little bit deviation is also there. There are many examples of drug which may have molecular weight greater than 500, also 600. But if 2 or 3 conditions don't get satisfied, then you have to be very careful. If one condition doesn't get satisfied, sometimes it may be okay, but if it is 2 or more, then you have to be very careful. Okay, so I'm saying, some malarial drugs, antiviral drugs, they may have very high log P, but still it is used as an antiviral drug, although it doesn't satisfy Lipinski's rule. So if one of the conditions doesn't get satisfied, it's okay. But if it is more than one, then you have to be careful. So look at this. They said number of hydrogen bond donors less than 3, acceptors less than 3, whereas Lipinski's rule had some other 5 and 5 and other. Then polar surface area 60 angstrom square. Okay. Then we have Han et al. Rule, bioavailability greater than 30%. So different rules are there. Okay, so different rules are there, which can help you to sort of approximately get an idea about whether a molecule can be a drug. We call it drug likeness property. That is the properties like absorption, distribution, metabolism, excretion, bioavailability, toxicity, side effects. So whether it will have all these conditions satisfied. Okay, we are not talking about activity, because activity is a different thing, but here we are talking about the drug likeness property of the molecule. Okay, there are many databases and web servers are there which can help you to calculate this drug likeness property, or sometimes they also have data, experimental data of some properties, so we can take it out. Okay, I am going to show you some of them. Okay, there are some databases which I have listed here. So if you get time, all of you, look at all these. I will show you some of these databases: Zinc database, Drug Bank database, drugs.com, FDA, ChemSpider. Please look at this. You can take a screenshot of this. So these databases give a lot of properties of many molecules. You can take a screenshot if you want. And then there are some databases or servers like Swiss ADME, ChemDes, pre-ADMET. I'm going to show them. So they calculate theoretically some of these properties. So please take a screenshot of this if you are interested. So they give you either experimental properties stored in, or they calculate these properties. Swiss ADME is very good. Pre-ADMET, I will show you some of this today. They calculate some of these properties. These databases like Zinc, Drug Bank, all these have some data already put in from experiment collected over from different literature. Okay, so we will look at some of them now. These drug bank drugs, they have information only about drugs. Drugs means it's already approved by FDA. FDA is Food and Drug Administration of United States. Similarly to that, we also in India, we have Drug Controller Authority. You must have been hearing it in the past 4 or 5 months. They have to approve whether a molecule can become a drug. Then only you can sell it as a drug. So FDA, so Drug Bank, drug.com, they have only drugs, approved drugs. information. Zinc is a database which contains several million structures and properties. Okay, it's a very huge structural database, very, very useful for you. We will be using it tomorrow, day after, and so on. Okay, that's called the zinc database. Okay, so now we'll look at some of these databases. It's called zinc 15. Yeah. Okay. Can you all see this?
Yes, sir.
Okay. So this has got almost 230 million structures. So not only drugs, but many other things. If you want only drugs, you have to go to drugs.com, drugsdb database. But this has a lot of structures. What is the use of this? We can get structures. We need the structures. If tomorrow I'm going to show you pharmacophore modeling, QSAR, docking, so I need to know the structure of molecules. So I need to get structures. Number one. Number two, it gives you some of the properties, some of the descriptors. I showed you, properties, descriptors, which I showed you. It gives you some of the properties, descriptors. Number two. Number three, it's also purchasable. So if you are interested in some molecule, you can purchase them, pay them money, and buy them. Of course, you can also synthesize in your lab, but if you are interested in some molecules, you can purchase from them. So it's a huge 230 million molecules. That's a huge one. So let us, we can search, for example, substances. This is the substances it says. So I'm going to tell aspirin. I know what is aspirin used for. Aspirin, you all know. Okay, so okay, this is aspirin, is acetyl salicylic acid. Okay, so this is aspirin. So you can see this is acid. This is the acetyl group. This is the CH3CO is called acetyl group, and this is the acid group, C double bond OH. So this is a benzene ring. So this is aspirin, a small structure, and some properties are given. Not all properties. Whatever experimentally reported, they put it in the database. But if you want to calculate, I will show you some databases like Swiss ADME. I will show you that. Some properties, as you can see, hydrogen bond donors, hydrogen bond acceptors, total polar surface area, 66%. So the polar surface area is very large, molecule is very hydrophilic. So it will not cross the GI membrane because you want it hydrophobic. But if the polar surface area is very low, the molecule may cross the GI, but it will not be water soluble. So generally, they say about 80, 90, 100, 120. 80 to 120 polar surface area, angstrom square, is good. So as you can see, generally, okay, so this is 66, aspirin, rotatable bonds. So some properties are given, you can see here. Okay, number of heavy atoms. Okay, this is called aspirin. Okay, aspirin has used for inflammation. Okay, let's go for say metformin. You all know metformin. Many people take it for diabetes. Yeah, this is metformin coming in. Yeah, metformin. Metformin is highly polar because so many nitrogen groups. You can see the structure, right? So many Hello, can you hear me? Hello?
Yes,
Yes,
sir.
sir.
We can hear you.
Okay, power went off somehow.
Yes, sir.
Okay. Okay, this is metformin. Can you see this metformin structure?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
and metformin has a lot of nitrogens here, so it's hydrophilic molecule. Okay, you can see hydrogen bond donors are 4. Charge, it's also got some charge because this nitrogen here these nitrogens can get charged. H can go away. So it gives you some properties. Zinc is a very useful database. We are going to use that tomorrow, day after, and so on. We can download the structure. Okay. Using zinc. Okay, the structure of this molecule can be downloaded. Yeah, here. There is a very useful database called Swiss ADME. It does a lot of calculations also. It can calculate a lot of properties. It's called Swiss ADME because after all, zinc gives you only few parameters. It doesn't give you all the parameters. So how do I translate structures from one place to another? So there is something called SMILES. Can you see this SMILES? Can you all see SMILES?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay, let me explain what is SMILES. SMILES is I can't see these structures. I don't know why. Okay, SMILES. It's called Simplified Molecular Input Line Entry System. Okay, so atoms are represented by standard abbreviation of the chemical elements in square brackets. Gold is AU. So carbon means C, nitrogen is N, O is oxygen, like that. You represent them. Okay, these you do not represent in a bracket, whereas AU, AG, that is silver, you represent in a square bracket. Okay. Another thing is hydrogen you do not represent. It is automatically taken in automatically based on the valency. So for example, if I write O in SMILES, it means water. That means H and H is already assumed. So it is considered as HOH. If I write just C, if I write only C, that means it's methane, CH4. Okay. So that's the advantage of SMILES. So we can represent it as a text form. So for example, cyclohexane. So I represent it as a C, 6 carbons. And when I put 1 and 1, that means this carbon and this carbon are connected because it is cyclohexane. Okay. Dioxane means C. There is a O, and this O and C are connected. Okay. That's called a dioxane. So once more, when I put C, capital C, that means methane, because hydrogens are not represented automatically. It is taken care of. It's CH4. If I put O, that means water, H2O. Okay. And if I put CC, that means it will take it as ethane. If I put CCC, it will take it as propane. Okay. So that is a single bond. If I want to mention a double bond, then I have to put a C equal to C. Equal to sign is there in our laptop. Okay. So it is taken as double bond. That means that is taken as ethylene. Triple bond is taken as hash sign. Hash sign is available also on our screen, actually. So if I want to put methanol, I'll put CO. C means CH3 taken. O is automatically OH. So that is methanol. Ethanol means CCO, because the first C is taken as CH3, second C is taken as CH2, and then the OH. So the advantage is we can represent, we can get any structure written as a text form. That's the main advantage of even cyclic structures. Aromatic, how do you represent? You represent in small c. So benzene is small c with 1, that is closed, whereas aliphatic cyclohexane, big C connected. You understand? So if it is small c, so pyridine, there is a small nitrogen and there is an aromatic CCCC. So when you represent in small c, that is aromatic. When you represent in large c, that is aliphatic. So aromatic can be represented, aliphatic can be represented. All these could be represented. That's the advantage of this particular Smiles notation. And the main advantage is I can copy structures from one website to another website. That's another advantage. Okay, for example, I want to copy the Smiles notation of metformin. You can see this Smiles notation of metformin from zinc database. I can take it to, again, you can, I have copied the Smiles notation of metformin from zinc database. You can see here into the Swiss ADME. Swiss ADME does a lot of calculations. So I have copied that and then I say run here. You can see this run. When I say run, it does a run. Okay, it's done. It has done a lot of calculations. You can see the calculations.
Yes, sir.
Okay, good. And so you see, I mentioned about GI absorption here. GI absorption is good. Blood-brain penetration is no. PGBF flex, I talked about so many structural features, descriptors. Then cytochromes. Cytochromes are some enzymes which they are oxidoreductase, which degrade any material, especially they are found in your liver. So whether it is getting degraded, then it also gives you the bioavailability score. Look at this bioavailability score. So it tells you good bio 0.55, 55%. That's very good. Lipinski's rule, all these rules I said about Lipinski's, Goes et al., Weber rule, so many rules are there. So does it satisfy or don't satisfy? So all those things are also given here. Then it tells you the total polar surface area. Okay, total polar surface area is also given here, 88. It's a little bit polar. Like I said, many nitrogens are there in this particular thing. Hydrogen bond donors, hydrogen bond acceptors. Okay, formula, so many things. Then log P is given here. It's a hydrophilic molecule. That's why log P is low. If you take a hydrophobic molecule, log P will be much higher. There are many ways of calculating log P. Many softwares are there. So many softwares give different answers. Okay. So this log P from different methods are there. So Swiss ADME is very useful. You can practice. Go to zinc database. Select a molecule. You can copy the Smiles notation. Okay. You can copy the Smiles notation, then take it to Swiss ADME, copy it here, okay, and then this is the structure of metformin, and then it does a lot of properties. It gives you solubility data, good solubility, highly soluble. So it gives under that class of solubility, and then so many things. properties it is calculating, which is very useful for you. We can also draw the structure here. Okay, so if molecule you don't have it in zinc database, I can draw the structure here. You can see this. I can draw structures here. So this is a structure. So I can draw structures, and then I can ask it to calculate the smiles also for this. Okay, this is called chalcone. Chalcones are found quite a lot in natural products. They have very inflammatory properties. They have bacterial properties. Okay, so 2 benzene rings, and then this unsaturated. They are called alpha beta ketone unsaturated. So if I click on it, it will put the smiles notation for this. I will remove this. Voila. Then I can put the smiles. Yeah, it put the smiles of this, and then I can say run. So it will run it, and it will give the properties of the molecule. Here it is. Okay, it gives you all the properties you can see. Gives you Lipinski's rule, satisfied rules. See, look at the polar surface area has come down. If you remember, for the metformin, it was very high. And here it's very low because it's very hydrophobic molecule. It's got aromatic, CH2. Then there is only one oxygen, that is only hydrophilic. Rest all are hydrophobic. That is why total polar surface area has come down. GA absorption still good, it says. So solubility, it says soluble. It doesn't say highly soluble. If you remember metformin, we got highly soluble. Here it's soluble. Like I said, it's a hydrophobic molecule. GA absorption, of course, is high because hydrophobic molecules will have. Log P again has gone up. If you remember metformin, it was 0.77 or something. This is 2.54. Log P has gone up because it's a hydrophobic molecule. So Swiss ADME is a extremely useful software which does a lot of calculations, property calculations. So if you think one molecule, the solubility is not good or something like that, then we can do some, we can modify the structures also. Let me take this, import. Smiles. So I imported the same molecule. I want to make it a little bit more hydrophilic. So I may put a OH here. Okay, so it's become a little bit hydrophilic because I put an OH. Okay, so then I can see how the properties change. So I can do a little bit of lead optimization using this Swiss ADME. Okay, now I can say run. So I put an OH there. So I made it a little bit hydrophilic, and then we see how the things look like. Okay, so change has happened, right? Total polar surface area, some change has happened. It's improved. Okay, then if you look at bioavailability also, okay, some solubility might have increased. Okay, these numbers would have changed. So I can look at different modifications. If it is too much hydrophobic, I try to make it hydrophilic. Too much hydrophilic, I try to make it hydrophobic. Like that, I can make the structure changes. I can add OH, or I can add NH2. So many things I can do actually using this, and then again recalculate, and then see how the properties look like, and so on. Okay, that's the another advantage with that. Of course, we don't know whether as a chemistry person able to synthesize these molecules, because only a synthetic chemistry person will be able to tell us whether he or she can synthesize this molecule. But at least on the computer screen, we can do a lot of these modifications, adding many things actually. Okay, so this is a very useful server. Okay, we can copy from zinc, put it here, and then do a lot of calculations. Okay. Okay, I will show you another one. Again, I'm going to chalcone, and chalcones are found quite a lot in natural products. And okay, these are called alpha beta unsaturated ketone structure. A lot of natural products. Even if you look at that particular combination of alpha beta unsaturated ketonic structure is found in many natural products, which have many biologically useful properties actually. Okay. Okay, now I'll show you another software. So these databases, take a screenshot of all these. The Swiss ADME I showed you. I'm going to show you this software which can calculate toxicity. Okay, it can calculate toxicities. So that's also a useful software. All the interesting point is all these are free, so it's very useful for teachers. It's useful for students project, and so on. So whatever I'm going to show is all free. So we can draw the structure also here. That's the beauty of it here. And we can also import structures. So we can load molecule. So you have to load a molecule in mol file. How do we get the mol file? I'll show you how to get the mol file. If you go to zinc, zinc gives you SDF file. So I will, there is a software, another software I will show you, which converts SDF. So it's downloaded that. Okay, so I've said that somewhere. Yeah, chalcone here. I've said that. Now there is another. I need to convert into mol file because the pre-ADMET wants everything in mol file. So how do I convert that? So as you can see here, you can read this, it wants in mol file. So I am going to convert that. There is a very useful another software called OpenBabel. OpenBabel, can you see that? OpenBabel. Again, this is also very, this is also free. Okay, this is a free software. Can you see this? Can you all see this?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So this is where we give the input left-hand side and we get output. So many different formats. As you can see, so many different formats and so many different output formats. So this is very, very useful for our drug discovery. SDF format, note that. SDF format, mol format, mol2 format, MOPAC format. So we need all those formats for our various studies in the next 3-4 days. So that's the advantage of that actually. So look at this. I am going to get the SDF format of that. Okay, SDF format. Okay, SDF format. So I'm going to read that chalcone. Desktop. Yeah, chalcone. Yeah, this is the structure. This is the data of chalcone. I'm going to convert that into mol format. This is the mol format. Output below. I'll put output below. Okay. Then I'll say convert. Okay. So this is the mol format of that file. If I want, I can save it also, but I will just copy paste into that. Yeah. So I can copy paste into that. It's not working today. It's not working.
Hello, sir.
Yeah. Yeah, it's
So
not working. Yeah.
dot SDF, you can just change it as dot MOL and click enter. Then you can open with Notepad and just copy paste, sir.
Yeah, yeah. Man, that also I can. Let us see. It's. I think it's not copying properly.
Okay.
Okay, output file. No. Okay. Sometimes it works, sometimes it doesn't work. No. Okay, we'll try. I will find out the problem. So we can draw structures here. I'll draw the chalcone here, no problem. Okay, so I can draw structures also, and then we can say submit. Yeah, so it gives a lot of toxicity, skin toxicity, skin irritations, AMS toxicity, CACO toxicity. So as you can see here, so different types of toxicities it gives you. Okay. And similarly, we can do drug likeness property. Okay, again, still it's not coming this time also. Okay, so again, drawn and then submit. Now it gives you a lot of drug likeness property. All the rules. You can see these lead likeness rules. So many different types of rules. Rule of 5, that's the Lipinski's rule of 5, suitable. Okay, so rule of 5, violations. So different types of rules it gives you here. We can even download this. Then ADME properties. I don't know why the hell it didn't. Okay, now it will do ADME properties, submit. So ADME talks about absorption, distribution, metabolism, excretion, and so on actually. Okay. Yeah, so blood-brain barrier, how much it is, buffer, then CACO. CACO cells are your stomach epithelial cells. So a lot of studies are done for absorption using CACO cells only. And then it gives you cytochrome P. Like I said, these are the oxidoreductase enzymes which try to degrade your molecule. So is it going to be degrading that? PGB, is it going to get in? Okay, log P, log D. Log P is hydrophobic, hydrophilic balance. Log D is when the molecule dissociates. Like if it is a salt, it may dissociate into the anion cation. So log D will, but it will not dissociate in the octanol, because octanol is hydrophobic. It will dissociate in water. So log D is calculated based on including the dissociation also, whereas log P is calculated not based on the dissociation part. So log P and D is slightly different. So it calculates that also. Okay, so many different properties, ADME properties it's calculating. So this is again a very useful software. Then I said drug banks. These are very useful because before I start on doing a research on any disease, I may be interested to know whether there are any drugs already available for that particular disease. So we need to look at the drug bank, drug DB softwares. Okay, so this is called drug bank software. So we can give. So we'll know exactly whether any drugs are already there in the market for the particular disease which we are looking at. Say I'm looking at a particular type of cancer, skin cancer. Are there any drugs already available? What are their properties? And any side effects reported. So these are all experimental, FDA approved data, FDA approved drugs only. So these drugs, DB, drug bank, they're all only that. Unlike zinc is just a database of millions of compounds actually. So it gives you a lot of information about aspirin, all experimental information, any side effects reported, is there any drug interactions, all these are given actually. So it's a very useful data to have before you start your research. This is called drug bank. So similarly, we also have the other one. drugs.com. This also gives a lot of information about this. Then FDA gives the actual FDA database. What are the drugs that are in market? What are the drugs in clinical trials? Because again, that's also useful. It will tell you what are the drugs in clinical trials and what are the drugs which have been approved as of now. Okay, so that database is also very useful. Any side effects reported. So all those information may be available in that FDA database. Okay, this is US Food and Drug Administration. Okay, FDA takes action to address coronavirus, blah, 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 all those things. So we can search giving known names, or we can give disease name, and then we can do the search. Okay, so that's the drugs in market that is approved by FDA. If there are any drugs under clinical trials, even failed drugs will also be put in. So you will get a feeling of what are the types of failures that has happened in various drugs. So that is a very useful knowledge to have actually. Then we have the PubChem database. Okay, this site, maybe sometimes sites cannot be reached, so that problem could be there. So many different databases. We talked about Open Babel. Just like a Swiss ADME, pre-ADMET, which I talked about, another useful thing is called ChemDes. It also calculates a lot of properties of a molecule given a structure. Okay, this is a test, and it gives you properties of molecule or descriptors. So properties, structural features, structural descriptors, all these are the same. Okay, so it gives you a lot of descriptors, different types of descriptors. It's useful when we are doing quantitative structure activity relationship studies, where we are trying to develop activity with some descriptor. So it calculates many types of descriptors. Okay, so as you can see, thousands of descriptors. Descriptor is nothing like property. Like for us, our descriptors are like height, weight, length of my fingers or length of my arms, okay, size of my head or size of my palm. These are all descriptors. Okay, maybe color of the skin, color of the nails, color of my hair. So like that, for human beings, we can have at least 1,000 descriptors. Similarly, for molecules also, we can have thousands and thousands. Actually, 2,000 descriptors we can calculate for molecules, like molecular weight, number of hydrogen bond donors, number of hydrogen bond acceptors, log P, solubility, pK, pKb, total polar surface area, rotatable bonds, all number of carbon atom, number of nitrogen atoms, number of double bonds, number of triple bonds, number of aromatic groups, number of heterocyclic group, number of bromines, iodines. So these are all descriptors for molecule. Some descriptors may have effect on the activity. So like that, so for example, if you take a human being, somebody who has very high, big weight, may be able to be a good weight lifter. Okay, so that descriptor is useful to understand whether a person can be a good weight lifter. So a person who does not have much weight may not be a good weight lifter. Maybe a person with high weight, body weight, may be a good weightlifter. So that descriptor tells he or she can be a good weightlifter. A person who has got long legs, maybe very tall, long legs, maybe can be a good running race, can run fast. Okay, of course there are exceptions also. A person who is tall may be a good basketball player. So that descriptor of tall persons may be a good basketball player. Of course there are one or two short persons, but generally tall persons can be a good basketball player, or basketball players are generally tall. Good weightlifters are generally heavy, or they have very high weight. Like that, there is a relation between human descriptors with their human activity. Okay, so similarly for molecules also, we can have thousands and thousands of descriptors calculated using different softwares. Like I said, I showed you Swiss ADME, I showed you ADME tox, pre-ADMET, and then this ChemDesk. So all these can calculate descriptors, and then we try to relate which descriptor matches with which activity. So you can say input, it says input your smile. I think I'm putting aspirin. Okay, then I can say submit. So this ChemDesk also can calculate 1,000 descriptors. So say it has calculated many descriptors. So this is useful for QSAR, quantitative structure activity relationship studies. Okay, it's very, very useful. Like I gave about the human, and descriptor was a certain activity. Tall person, good basketball player. Heavy person, maybe a good weightlifter. Somebody who has long legs, maybe a good runner. Okay, in athletics. So many different types of human descriptors matching with their activity. Similarly, we can also try to find out which descriptor matches with the certain activity which we are looking at. That is what QSAR is all about. We will look at it later, actually. So these softwares do a lot of these descriptor calculation. So you saw Swiss ADME, which tells you, it calculates various rules, which I showed you, and then tries to say whether the molecule satisfies those rules. And descriptor calculation softwares like pre-ADMET, ChemDesk, and then many other softwares which I have shown in that list. Okay. There is a software called Dragon. So all these can help you to calculate descriptors, which are very useful for us to do the quantitative structure activity relationship type of studies actually. Okay. Okay, so smiles, as I said, is very, very useful if you want to transfer text-based structural information, like from zinc into Swiss ADME text-based structural information. If you want to transfer the structure itself, we have the SDF format is there in zinc, which can be taken to Open Babel. We'll look at it tomorrow for many other things, and then we can modify. But Smiles is text-based copy-paste into various databases. We can use take from zinc, go to Swiss ADME, or we can go to ChemDes and so on, copy the structure, and then do all these calculations. All these softwares also can, not softwares, these okay, can also help you to draw the structures. All of them have that feature also. That's the another advantage. We can draw our own molecule like Swiss ADME. They all have, as you can see, we can draw the structures. Swiss ADME, zinc, we can draw the structure. Many places we can draw our own structure if it is not found in zinc database or some other database. We can draw the structure, and then we can get the Smiles notation, and then we can calculate the properties using different types of databases. That's the advantage of all these. So so all these descriptor calculations are very useful. Okay, this is another server which can do descriptor calculation. It's called OChem. Okay, online chemical database. So this also can do a lot of descriptor calculation. See, properties are there, so we can calculate properties. Okay. Okay, so as you can see here, a lot of things are there. Melting point, log P, octanol water, so log D, so many things are there. Okay, so it can calculate so many different properties of molecules. So this is also a very useful database. So as you can see, almost 477 properties it calculates. So this is another useful server. That's called OChem. Okay, ChemDes we saw. Swiss Dragon is another server which gives you a lot of properties of various molecules. Then we have the toxicity checker, which also gives you toxicity of molecules. Okay, so we can draw a molecule and we can check for toxicity again. So all these are free, so they ask for all these information. Okay, so let me not go into that. So we can use this also for doing toxicity checker. So this set of databases which I mentioned here help you to calculate descriptors, help you to calculate the ADME properties, help you to calculate toxicity properties. But all these are properties. That means it's a theoretical number based on some equations. If you go to these databases, zinc database gives structures of several million compounds. It has got some properties, very little number of, but they are all experimental properties. So whatever zinc has, drug bank has, all these, they may have some properties like a total polar surface area, rotatable bonds, but they're all experimentally derived. And FDA database, drugs database have information about drugs that is existing, which have come into market, or even drugs which have failed because of some reason, or FDA will also have drugs which are being tested, okay, under clinical trials. So if you are going for looking at a new type of disease, you may start looking into these databases first, that is drug bank, drug.com, FDA databases, okay, and then you decide on what type of molecules you are going to look at. Okay, that should be your approach. Once you decide on what type of molecules, we can go to Swiss ADME, we can go to pre-ADMET, we can go to toxicity checker to look at various properties of the molecules and see whether it's going to have some adverse properties. Then modify these structures and then again redo the calculations and decide on some molecules which looks promising. Okay, then you may go into real experimental wet lab studies. Okay, this is how the entire approach is going to be. So the properties are very, very important. Okay, properties are very, very important before you decide on going into your wet lab, or even for animal studies actually. So different types of properties which I talked about, almost 2000 properties can be calculated with all these web servers which I have showed you. So you can also practice them in your home, okay, today. And then tomorrow we will talk about ligand-based design. One of the ligand-based design is pharmacophore modeling. Another ligand-based design is QSAR-based modeling. So we will look at all these in the next 2 succeeding days. And finally, on the last day, 4th day, we will look at target-based design, which is docking type of studies. Okay, so we will stop today with this, and tomorrow again we will continue. We'll look at the pharmacophore-based design. Okay.
Thank you, sir. The session is open for queries. The participants who have queries can ask.
Okay, otherwise you can even write it and give it to organizers, because if there are too many queries, it may be difficult. If you write it and send it to organizer, they can collate and also send it to me.
Sir, good afternoon, sir.
Good afternoon.
Sir, I have one query, sir. Suppose if we are doing drug repurposing, in that time, is it necessary to do all those properties, check all those drug properties for drug repurposing?
Yeah, so you must be reading a lot of news in the past 4 days. What happens is, although it is repurposing, it may have toxicity for some other disease. For example, it may be a drug for diabetic, but if you are repurposing for some cardiovascular, it may be when they test it on cardiovascular patient, it may be toxic for them, for cardiovascular. Okay, so but you don't have to do all the properties, because we already know its bioavailability, we already know Lipinski's rule, but toxicity can be different. Okay, but other properties you don't have to bother. So they may skip animal studies, but they may go for human volunteer studies directly. But toxicities can be different. Like I said, anti-diabetic drug, if it is being tested for, say, cardiovascular or something, if they are given for cardiovascular patient, it could be toxic for them. But other properties we don't have to bother. Yeah, agree.
Hello, sir.
Thank you, sir.
Yeah.
Sir, what about the HERG inhibition from HERG inhibition from pre-admit?
Herd inhibition, those data are not there. There are no genetic based data there, but cytochrome based data is there. A lot of cytochrome, and many of the genetic variations are because of changes in the cytochrome. So one needs to know which cytochromes are different. For example, in Asian population, which cytochromes are predominant. In say Caucasian, which cytochromes are predominant, and we can do whether there are going to be inhibition in certain cytochromes and some other cytochromes. So, but not, it's very difficult without doing clinical studies.
Okay. Sir, is there any online server to do screening of all molecules from like PubChem or Zinc based on the structure?
Oh, yeah. All these we can screen. Many of them will take multiple molecules. Yes, we can do that.
Okay. So please discuss about them also in the forthcoming days.
Yeah, because all these are single molecule. But if you want to do many, then if you have in your college one of these supercomputers or node based computers, you have to write a program to do that. Actually, these
Okay.
softwares.
So there are no other servers available for that.
Not with using these free softwares, but if you are buying commercial softwares, they allow some sort of a multi-node user approach. There are commercial softwares which can do ADMET with the multi-node approach, but we are talking about free softwares. So the whole thing is about free softwares, no commercial, because each commercial will have its own advantages, disadvantages. Free software you can choose based on your experience, knowledge, and requirements.
Okay. Thank you.
But for example, if you take Autodoc, which is a free software for talking, you write your own nodal multi-node front end, so that if you write a 16 multi-node, then there will be 16 Autodocs. You can put in 16 molecules and do simultaneously. Okay, so like that we can do. So you write the front end of it if you have your nodal system.
Sir, good afternoon, sir.
Good afternoon.
Sir, I have a question. Sir, in case of nanoparticle-based drugs, there is something called as protein corona formation. Is there any databases that discuss about this protein corona formation? And is PPG efflux similar to protein corona formation, sir?
Yeah. We can look at it. Yes, there are some things which can look at protein corona formation also. But here our focus is not on those. It's more of a ligand based, that is small molecule, and then target based, that is docking of small molecules to the target. And then of course one can do molecular dynamics and that sort of thing actually. But this focus is not more of molecular. It is not more of a molecular modeling type of stuff.
Yes, sir. Yeah. Thank you so much, sir.
Thank you. Hello. Yeah.
Sir, what is the website to study the toxicity of the already available subject? You have been telling us, sir, one drug may act toxic for another purpose.
Yeah.
But is there any website that can tell the toxicity, sir?
No, the point, the toxicity. See, like I said, if there is a drug already for diabetic and it's being tested on patients who have cardiovascular, the cardiovascular system and the reason for the disease of cardiovascular are very different, the mechanism. So the same drug which may be working for diabetics for patient A might not work for a patient B because of some toxicity related issues also, right? Because the mechanism of the person is getting a cardiovascular disease because of certain inhibitors related to angiotensin converting enzyme or beta blockers. So that may lead to some other toxicity, which we don't know unless there are some studies like volunteer studies or animal studies done. So that could be different. That is the reason why you must be reading about quite a lot. People with some other comorbidity may be finding toxicity for already existing drugs, right? So So many drugs are already, all the drugs that are being repurposed are existing for some other disease. But when I test it out on some other disease, the mechanism of action are different. The morbidity of those patients with those diseases are different. So that could lead to some other toxicity.
So
And
there is no,
especially with comorbidity, there could be some issues.
so we have to study in the experiments. So we cannot do it computation, right, sir?
We cannot prove it unless we know the mechanism
Yeah.
of the action. So suppose I am looking at a particular, I have a anti-diabetic drug, and I am looking at targeting some other enzyme in the cardiovascular region. Then I know those targets. Then I can look at docking and I can see how it is. But the toxicity part we cannot really explain through computation.
Thank you. Thank you.
Sir,
Yeah.
is there any online tool or software for screening antiviral compounds?
Antiviral compounds.
Yes.
You go to zinc and pick out all viral molecules. No, you can do that.
Other than that, is there any other tool?
On viral.
Antiviral compounds, sir.
You want the compounds as such, is it?
Yes, sir.
No, there are no tools per se. No, but you can take out. After all, zinc database contains almost 180, 200 million compounds. You can pick up all the viral structures and store it in some database, and then you can have auto dock or something and try to dock with that. No, that you can do.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Okay, we'll see tomorrow.
Thank you for your valuable information. And participants are requested to submit your feedback link or attendance link, whichever provided in your Google chat.
Okay.
Thank you, sir.
Thank you.
Participants, once again, I'm repeating, please click on the attendance link and provide your attendance. Only if you provide your attendance, certificate will be issued.
Madam, sorry.
Yeah.
I just want to. I had some problem with some slides. I want to just put. You can see whether it's
Okay,
working.
sir. I'll be joining in another 1 hour, sir.